Section 2.1 is linear relations, and we're going to start by talking about graphing. Plotting ordered pairs for x, y. I know you remember a lot about this graph, but just to make sure everybody's on the same remembering page. This is our x-axis, this is our y-axis. One way to keep track of the order of the ordered pairs is it's alphabetical. It's x and then y. The right-hand side's positive, the left-hand side's negative, and the top is positive and the bottom is negative. So what we're going to do is we're actually going to plot some points. So we have A, B, C, and D. If you have grid paper, you're welcome to use that as you're plotting things. Otherwise, just make sure you're being very careful as you're plotting so there's no guesswork on did they really plot the right point kind of question. The first point listed is 5, -2. In fact, my biggest number is 6. So I'm going to go 6 in all the directions and try to space them out as evenly as I can. It won't be perfect, but we're trying to get it spaced as best as possible. Yeah, that was definitely not good. Okay. Cool. All right, so the first one is 5, -2. So we go in the x direction first, left and right. So we go over 5. So this would be 1, 2, 3, 4, 5. And then we go down 2. So we'd be at about right here. So over 5 and down 2, and we're going to label it with the letter A. So that we're at point A. Get that a darker red. All right, the next one, B, is -5, 3. So -5 means I'll go left 5. +3 means I'm going to go up 3. So left 5 and up 3 puts me about right here. And that's point B. The next one is -1, -2. So -1 is left, -2 is down. So we're about right here. That's point C. And then 6, 2 means I'm going to go to the right 6, and I'm going to go up 2. Looks like I'm about right there at D. Okay, so graphing. Do you guys remember ordered pair graphing? Wonderful. Okay, moving a little bit further into that area, we're going to talk about linear equations. So linear equations are those that have the form or have the ability to have the form y = mx + b, or simply y = b or x = b. There's 3 different types. M and b are constants. So there's some number, don't know what they are necessarily until I am given an equation, but they're just a number. And the first thing we're going to do with our linear equation is to create some ordered pairs. So this chart is going to be a chart for the equation y = 5x - 2. And then we're given 5 different x values that we're going to evaluate our function at. So the first one is -2. So this is 5 times -2 minus 2. So what is 5 times -2? -10. And -10 minus 2 is -12. Okay, we're going to go on to -1. 5 times -1 minus 2. So what is 5 times -1? -5 minus 2? -7 is right. Now we're going to do 5 times 0 minus 2. 5 times 0 is? Minus 2? -2. 5 times 1 minus 2. 5 times 1 is? 5 minus 2 is? 3. And then 5 times 2 minus 2. 5 times 2 is? 10. Minus 2 is 8. Okay, so you don't have to show all of this, okay? I'm just reminding you that's where I'm getting my numbers from. Take a look, though, before you flip your paper over. You're all flipping papers. Do you notice the pattern that's happening if you just consider these numbers that I have on the right-hand side? Yeah, they're increasing by 5. And that's actually happening from this 5 right here, and that 5 is known as the, do you remember? Slope. Slope. So we'll get into that in just a second. But you'll notice what's happening over here is that the x is increasing by 1 every time, and then the y is increasing by 5 every time. And that's actually happening due to the 5 right there. Distance. This equation looks so much messier than it really is. The distance equation says that I find the difference between the x values, and I square it, the difference between the y values, and I square it. I add those values together, and I take a square root. Okay, you ready to do an example? Okay, I'll rewrite the equation over here because we're going to need it anyway. Okay, so we have two ordered pairs given. We have the value at the point A as 2, -3, and point B as -2, 1. And it doesn't make any difference which one you label as x1, y1, and which one you label as x2, y2. Okay, so I'm just going to go in order. This equation for finding distance tells me that I'm going to take the first one minus the second one. So 2 minus -2. And I'm going to square it. And then on my y values, I'm going to take the first one, -3, minus the second one, so -1, and I'm going to square it. And then I need the square root over that whole quantity. Okay, integers, right? That's what this is. We worked a lot back in the last section, or in the last chapter, unit, whatever, with integers. So what is 2 minus -2? That's 4. So this first part is 4 squared. How about -3 minus 1?
-4.
That's -4 squared. So what is 4 squared?
16.
16. And what is -4 squared?
Also 16.
Also 16. And we're back in the section of material 110 that was your favorite. It's radicals, isn't it? It is. So what is 16 plus 16? 32. Now, you can get a decimal approximation for 32, but that's not what this question's asking you for. It asks you to give an exact answer, which means you're factoring and you're looking for pairs that they have in common. So if I factor 32, how will it factor?
16 and 2.
Okay, 16 and 2. 16 is 4 and 4, or 8 and 2. So I'm going to stop with the 4 and 4 because they match. I don't have to keep reducing once I have a pair that matches. So this square root 32 is the square root of 4 times 4 times 2. The 4's match, so they can come out. The 2 does not have a matching pair, so it stays underneath. So this is 4 square root 2. Sorry, my space on my screen is more vertical. Your space on your papers are more horizontal. So just, restructure things.
4 times 2?
Yes, it is. 4 times 4 times 2.
And so when they match, it comes out.
Exactly. Anytime they match, it comes out. Kenny?
I feel like I remember this being the other way, so like x2 minus x1.
So let me show you something fun about this one right here, because let's say you did it the other direction. You don't need to copy this down. I just want you to watch what happens. So let's say we did it in the opposite order. And so we did x2 minus x1. So it would be -2 minus 2 squared plus, and then we did y2, which was -2, I'm sorry, y2, which is 1, minus negative 3 squared. So what is negative 2 minus 2? So this is negative 4 squared. And what is 1 minus negative 3? Positive 4 squared.
So it's still
So it's the same.
It's the same thing. And that's actually why at the beginning I mentioned that it doesn't matter where you put the x1, y1 and the x2, y2. So also sort of intuitively, take a look at what's going on here. I mentioned this when I was describing it. The distance formula is actually measuring distance between corresponding values. How far on a number line are 2 and negative 2 apart? They're 4 apart. One's 2 this direction, the other 2 this direction. They're 4 apart, right? That's the number I keep getting is 4, and then I square it. How far are negative 3 and positive 1 apart? Well, they're 4 apart, right? That's the other 4 that keeps getting squared. And because I'm squaring things, it doesn't matter whether you do the distance from, the bigger value minus the smaller value or the smaller value minus the bigger one, because when you square them, they all end up positive anyway. So if you think of it intuitively, that's kind of why it's not actually mattering which order we do it in. So you can pick your favorite order, or you can change it every single time, and it will still work out okay. Thanks for asking that. Yes, ma'am.
Okay, why can't, when we square the 16 plus 16, why can't they just come out?
Because they're added together underneath.
You can only do that if they multiply?
Correct.
Oh.
So what you're remembering is that if you had, if you had the square root of 16 times 16, you could pull it out.
Okay.
But that's not what we have. We have addition. And we have to do the addition before we can pull them out of the radical.
Okay.
So back in that section, we had what was called the product rule for radicals, and this is not a product.
Okay, sorry.
Yeah, no, it's a really good question because it's a common thing for people to try to do. Yeah. All right. Midpoints. That's our next one. The midpoint is the location on a line segment connecting 2 points such that the distance to each point from this location is equal. This can be found by x1 plus x2 divided by 2, y1 plus y2 divided by 2. So we're going to use the same ordered pairs that I used just a moment ago when I was finding their distance between them. So the distance was 4 square root 2. Midpoint actually is a cleaner calculation because I don't have any radicals, right? It's just addition and division by 2. It's averaging things is what it really is. So when I'm finding the midpoint, I'm taking the first x value. It doesn't even matter if it's the first one and the second one or the other way around. The first one plus the second one. So this is 2 and negative 2. Add them together divided by 2. And negative 3 and 1 added together divided by 2. So what is 2 plus negative 2? It's 0. And 0 divided by 2 would then still be 0. What's negative 3 plus negative 1? I'm sorry, negative 3 plus 1. Said it wrong. It's negative 2, and negative 2 divided by 2 is negative 1. So the answers don't have to turn out to be whole numbers, but often they will. Anytime your numerator is even and you divide it by 2, you get a whole number. Worst case scenario, your numerator is odd and you divide it by 2 and you get a 0.5. So the numbers are very friendly when you're taking a look at midpoints. It's always either a whole number, I should say it's always either an integer or an integer with a 0.5 on the end. All right, we looked at this definition before, but I want you to recall this definition. A value is a solution if it makes an equation true. Okay? So we did it for a specific value. Ours was x equals, or when we did it before, we had, I know what we're doing. Okay, never mind. We had a single variable equation. So we had things that looked like x plus 7 equals 5 plus 9 minus 7 or whatever, and we said, is 5 a solution? And we plugged the 7 or the 5 or the whatever in, and we said, yes, it's true, or no, it's not. So for what we're doing on this one, we may have one variable equations like this one, x equals negative 5. Or we may have an equation for a line that has two variables, an x and a y. So on all of these ordered pairs, the x value are the beginning values, right? Okay, and y values are the second values. So my equation for this one is simply the equation x equal negative 5. So I'm going to plug in each one of these into the x value. That's negative 4 equals negative 5. Is it true?
No.
This is false. We're going to have 6 equals negative 5. Is that true?
No.
It's false. And the last one I have negative 5 equals negative 5. Is that true? It's true. So what that means is that this ordered pair at the end is a solution, and the other two are not. You know, it sort of felt funny. And we're going to talk more about that particular line later. But the practical point that we're making right now is whatever the x is, whatever the y is, plug it into the equation and see if it makes it equal. If it does, it's a solution. If it doesn't, it's not. All right, here's another one now. This one has an x and a y in it for us to practice with. 2x plus y equals 7. So I'm going to have 2. X is supposed to be 1, and y is supposed to be 5. 2 times 1 is 2, plus 5 is? Does 7 equal 7? Yeah, so this one's true. Let's go to the next one. 2 times 2 plus 2 equals 7. So what is 2 times 2? 4. 4 plus 2 is? 6. 6 equals 7, true or false? That's false. And then our last one, we'll put it over here. 2 times 3 plus 1 equals 7. 2 times 3 is 6 plus 1 is 7 equals 7 is true. So in the last example we did, we had one of them was a solution and the other two weren't, right? This one, we happen to have 2 of them that are solutions. So there's not a specific number that are always going to work and not versus not work. They could all work. They could none of them work, or there could be some sort of combination of those there. So what it means is that, I'll write it down over here actually. These solutions, the ones that are solutions, were 1, 5 and 3, 1. And there's actually infinitely many more that I could have had given to me as well. But these are the 2 that I tried that worked. So they're both solutions. All right, so number 10 will be the most difficult, maybe, question for the grader to grade. Not because it's a hard question, but because every single one of you could have a different answer and all be right. Questions like that are hard to grade because I have to check every single one. I don't have this just real quick going back and forth. Did they get it? Pieces correct. This question says to find an ordered pair that's a solution to the equation. Find one that works. There are infinitely many ordered pairs that will work. Infinitely many. Some things are really nice, whole numbers. Some things are fractions. There's other values that you could get to, but none of you are going to do those because why would you if there's other options? They're easier, right? So somebody give me an ordered pair that you believe will work. Negative 1, 1. So let's check it out. If I do negative 3 times negative 1 plus 2 times 1, does it equal 5? It does. That's a solution. So that would be one answer and you'd be done. But let's say that you saw something different. What's another pair that would work? You guys are going to make it easy on the grader. Everybody's going to just pick the same one? I'll give you one. I'll give you a fraction. 0 and 5 halves will work. Negative 3 times 0 plus 2 times 5 halves equals 5.
Negative 3 and negative 2.
Okay, let's try negative 3 and negative 2. Daniel gave us. So I have negative 3 times negative 3 plus 2 times negative 2. I feel like my signs are going to be off when I do this, but, oh, no, they're not. So you had 9 plus or minus 4, and that one equals 5. Fabulous. Good job. Do you have one, Damaris?
I was just gonna ask, so you just basically guess numbers?
You can. That's one way you can do it. Daniel, did you guess numbers to get yours?
3 and the negatives.
Okay.
Coming up like 2, 3.
Okay, so you used small whole numbers to try and see what would work. Does that sound accurate? Okay. So a couple of things that are nice ways to guess numbers here, because you could guess a lot and never end up with something that worked, right? Like that's legit possible. Agreed? Yeah, it is. So one thing that you could do is that you could pick a value, because this is what I did for my example. I picked 0. I like zeros. They disappear things, right? I mean, if I put a 0 in somewhere, it eliminates a piece. So one thing you could do is you could put a 0 in somewhere and simply solve for the other part of the equation. So you could take this equation and just decide, I'm going to let x equal 0. Well, if x is equal to 0, then that's 0, and then I divide by 2, and I've got my 5 halves. Okay? But there's nothing special about letting x equal 0. I could let x equal 3. So let's see what would happen if x is 3. What's 3 times 3? 9. And if I do the 9 to the other side, I would be subtracting the 9. 5 minus 9 is negative 4. So this would actually give me a solution of 3, negative 2. This is why there's infinitely many solutions. And not only can I do that with the number or with the variable x, I could pick a variable for y instead and do the same thing if I wanted to.
So if you put in 0, you just do it to one of the letters?
Yep, you just pick one. And it's not really just putting it in for 0 specifically. You can put any number into any variable and solve for the other one, and you'll find a solution that will work.
Okay.
Yeah. So it could be awful. Don't be awful to the grader, but let me just give you an example. You could say, let x equal 52. You could. Please don't do that. This would be so mean. I'm sure the grader, she wouldn't quit, but she might think about it. Yeah, you could.
I'm gonna do that.
Don't do that.
Mess with y'all.
Negative 3 times 52 plus 2y. Let's just try it, because I want to show you that it will work no matter what weird stuff. This isn't super weird. But what is negative 3 times 52? Grab a calculator. Or maybe you can do it in your head. Yeah, negative, right? Negative 156. Okay, we can add 156 now. What's 156 plus 5? 161. Oh, wait, so this would be negative, sorry, not negative, it was positive, 52 and 161 over 2, and it would work.
Question.
Wait, and it
Could we,
Yep.
got a question like that? Could we make x an entire problem, like x equals parentheses, negative 30 plus like 4?
Sure, you could.
Oh, I'm gonna have so much fun with this.
All right,
I feel bad for you.
what I want you to understand is that there's lots of answers, okay? You can guess and check, okay? Guess and check was kind of what Damaris was asking. Did we just guess and check? Some of you probably did, where the very first example you guys did, you saw it. It was a nice, easy answer to choose from and to see that it worked very quickly. I like to put in zeros for things because things disappear and other pieces solve nicely. Maxwell wants to make it hard on the grader. That's not very nice.
Sorry.
Yes, Kenny?
So you can just pick one number, plug it into one of the variables, solve it, and then whatever you get for like y equals 9.
Would be the other value. Yeah. So the ordered pair here was that negative 1, 1. My ordered pair here, this is the answers. I'm boxing in all the things that are actually answers here. These are all answers. I already have the one up here boxed in. and this one down here. All of these would be solutions to that equation. And there are infinitely many. Literally makes sense now that I'm telling you, you can pick a number for any variable, either variable, right? And simply solve for the other variable. All right, so we're done for the lesson part today. So you guys have plenty of time to finish this lesson in class. And then you won't have any homework for tonight, right?
I love not having one.
I know.